Welcome again. Today we'll talk about hydrogeology in WASH. Today we'll learn about hydrogeology adventure in WASH. We'll delve into the fascinating world beneath our feet from underground layers of soil to reach our homes. Throughout our lesson today, we'll explore so many topics. First, we'll crack the code of groundwater exploration, unraveling how we can detect this hidden water. Then we'll discover the various types of aquifer, each with its own unique personality, to understand how they interact with groundwater. Next, we will review the aquifer and well performance test to ensure a reliable flow of water. We'll explore the difference between these tests and uncover the secrets they reveal about the aquifer's health and potential. Now comes the exciting part, well design and construction. We'll learn on a step-by-step about the construction process from start to finish. Also, we'll look at the diverse method of groundwater pumping. We'll delve into the world of pumps from basic hand pumps to the most advanced technologies. Finally, we'll explore the fascinating world of groundwater treatment and recharge. We'll uncover new concepts like aggressivity and the power of riverbank filtration. Throughout this incredible venture, we'll witness the profound connection between geology and WASH. Hydrogeological studies are the key to understand groundwater, the hidden treasure beneath our feet. These studies help us locate, manage, and protect these vital resources. Hydrological studies rely on multi-branches approach. First, we consult geological map, leading us to potential groundwater reserve. Next, soil studies or geotechnical studies tell us how well the land can store and transmit water. Finally, geophysical survey act as our high technological tool, using sound waves, electrical currents, or even gravity to create an image of the hidden world beneath the surface. Our mission of groundwater doesn't stop at the surface. Infiltration rate tests help us understand how efficiently water fills aquifer. Aquifer tests reveal the aquifer's health and potential to provide water for our needs. And don't forget the power of technology. Remote sensing and GIS allow us to analyze vast areas from above, identifying potential clues about hidden water resources. Geological maps are the foundation of any hydrogeological study. Imagine a treasure hunt without a map. It would be a frustrating endeavor. This map acts as our roadmap, revealing the distribution of rock formation, minerals, and most importantly, potential groundwater sources. So by understanding the types of rock present, we can predict their ability to store and transmit water. The presence of specific minerals can also indicate the quality and potential contamination of groundwater sources. Geophysical survey are like X-ray vision for the Earth, allowing us to study the subsurface structure without digging. Various techniques and instruments are employed, each with its strengths and limitation, and we will take a look at each one of them in the next slides. Seismic method utilizes sound waves to create an image of the subsurface. Think of beating the ground with vibrator and feeling the vibration travel through your feet. Seismic survey use a similar principle, but with sound waves traveling much deeper into the earth. By creating sound waves and measure their travel time and character, we can gain valuable insight about the subsurface. Seismic survey are like listening to the earth echoes, revealing information about the different layers of rock and their water-bearing potential. Just like some materials conduct heat better than others, rocks and water have varying electrical conductivity. Electrical method measure how easily electrical current flow through the ground. It uses the principle to create an image of subsurface. Electrical resistivity imaging measure how easily electrical flow through the ground. Clay and water conduct electricity well, while dry rock act as a resistor. By analyzing these variations, we can map different layers of rock and identify potential water-bearing zone. Also, certain minerals can hold an electrical charge for a shorter time, allowing us to identify their presence and potentially gather information about the water quality. Gravity method measure tiny variations in the Earth's gravitational field caused by variations in subsurface density. Imagine the Earth's gravity as a constant pull. Gravity methods are like incredibly sensitive scales that can detect tiny variations in this pull. Denser materials like rock exert a slightly stronger gravitational pull compared to less dense materials like water or air. By measuring these subtle variants, we can create a map of subsurface densities, potentially revealing the location of denser rock layers that may hold groundwater. The Earth has a natural magnetic field, and magnetic method uses this field or variation to learn about the subsurface. Certain rocks types, particularly those rich in iron, can cause variation in the Earth's magnetic field. By measuring these variations, we can potentially identify specific rock formation or locate metallic objects buried underground. While not directly indicative of groundwater, magnetic survey can be helpful in geological mapping, which can then be used in conjunction with other methods for groundwater exploration. Ground penetrating radar, or GPR, transmits high-frequency radio waves into the ground and measures the reflected signals. Similar to radar used in airplanes, GPR can detect variations in subsurface materials based on their reflection properties. Ground penetrating radar, or GPR, is like a high-technical X-ray for shallow depth. It transmits high-frequency radio waves into the ground and analyzes the reflected signals. Think of boreholes as a window into the earth. Borehole geophysics survey take advantage of this direct access to gather detailed information about the subsurface. Specialized instruments are lowered down in the borehole to measure various properties of the rock formation. Natural gamma ray logging measure the natural radioactivity of rocks, which can help identify different rock types and potentially assess groundwater quality. Electrical conductivity logging provide information about the electrical conductivity of the formation, aiding in the identification of water-bearing zones. Sonic logging measures the velocity of sound waves traveling through the rocks, providing valuable insight about rock density and porosity. By combining all this data about the borehole, we can get more information about groundwater potential. Imagine pouring water on the ground and observing how quickly it disappears. An infiltration test is a more controlled way of measuring this process. The double-ring infiltration test is a common method that involves digging a hole and inserting two metal rings. The larger ring helps us account for the influence of the whole side walls on the infiltration rate. Water is poured into the inner ring, and the time is taken for the water level to drop by a specific amount is measured. By calculating the rate at which the water level drops, we can determine the infiltration rate of the soil. This information is important for understanding how efficiently an area can recharge groundwater aquifers. Areas with high infiltration rate allow water to infiltrate quickly, while low infiltration rates may indicate need of alternative water management strategies. Now it's time to delve into the properties of the hidden treasure itself, the aquifer. Our soil classification system groups these particles into the main categories: gravel, sand, and fines. Fines mean silt or clay. Gravel, with its large pores greater than 2 mm in size, allow water to drain quickly. Sand, with its medium-sized pores less than 2 mm, can also store and transmit water reasonably well. Fines, on the other hand, less than 0.06 mm, have very small pores that can hold a lot of water, but they often restrict water movement. So let's delve into the key properties of an aquifer. The first property is porosity, the percentage of void space within the rock or soil. Effective porosity considers only the interconnected pores that allow water to flow freely. Finally, specific yield tells us how much of the stored water we can actually extract through wells. It represents the portion of the water that is readily available under the force of gravity. Now let's shift our focus on how easily water can move through an aquifer, a crucial factors for well yield. Here we will counter three key properties: permeability, transmissivity, and hydraulic conductivity. Permeability, the ability of a rock or soil formation to transmit fluid, including water. Imagine pouring water onto sand versus pouring water into clay. Sand, with its large and interconnected pores, has high permeability compared to clay. Permeability is a general term for the ease of fluid flow. Transmissivity. Think of transmissivity as the total amount of water an aquifer can transmit per unit width. A highly transmissive aquifer, like one composed of coarse sand or gravel, can allow large volume of water to flow through it. Hydraulic conductivity, a measure of the ease with which water can flow through the porous space of an aquifer materials. Hydraulic conductivity is a material property, while permeability is a property of the entire aquifer. Now let's delve into a few more properties that relate to the volume of water stored in an aquifer. Storativity. Imagine a sponge filled with water. When you squeeze the sponge, some water is released. So storativity tells us how much water is released from an aquifer relative to the change in water pressure. Specific retention. Think of a sponge that you have squeezed. Even after squeezing, the sponge still holds some water. Specific retention represents the water that is held tightly in the aquifer pores and cannot be readily extracted by gravity drainage. Specific storage tells us how much of the volume of the water stored in an aquifer change as the water pressure change. Imagine an aquifer as a container. The more space or void it has available, the more water can hold. Porosity is expressed as a percentage and is calculated by dividing the volume of void within the rock or soil by its total volume. And there are different types to measure porosity. One method involves comparing the bulk density of the entire rock or soil formation with the particle density of the solid particle alone. Another method focuses on measuring effective porosity, which consider only the interconnected pores that allow water to flow freely. Not all the water stored in an aquifer is readily available for us to use. A specific yield tells us how much of the stored water we can actually extract through wells. Imagine an aquifer as a giant sponge saturated with water. Specific yield is like squeezing that sponge and measuring the amount of water that drains out. We can determine a specific yield through field tests like pump test. Permeability is a qualitative property, meaning it describes the ease of flow, but not the specific rate of flow. There is no single clear cutoff formula for permeability, as it depends on various factors like pore size, porosity, and grain size of the aquifer materials. However, we can estimate permeability through field tests like pump test or laboratory tests. It's just like comparing water flowing through sand versus clay. Imagine an aquifer as a series of pipes. Transmissivity is like the total capacity of these pipes to carry water. It considers both the ease of flow through the aquifer materials, the hydraulic conductivity, and the thickness of the saturated zone. An aquifer with high hydraulic conductivity like coarse sand or gravel and a large thickness will have a high transmissivity, allowing it to transmit large volume of water. So T equal K times B. Imagine water flowing through large interconnected pores versus tiny pores. Hydraulic conductivity tells us how water can flow through these pores based on the material properties. It's a characteristic of the rock or soil itself, independent of the thickness of the aquifer. Storativity is like the elasticity of an aquifer, its ability to release stored water when the pressure changes. Imagine squeeze a water-filled sponge. Some water comes out due to drainage, a specific yield, and some comes out because of sponge itself compression slightly, specific storage. So storativity considers both these mechanisms and tell us how much water an aquifer releases from storage in response to a decline in water pressure. So storativity can be expressed as the sum of two components, specific yield and specific storage. Aquifers are not all created equal. They can be classified based on their permeability, which is their ability to transmit water. So aquifers is impermeable layer that does not transmit water at all, like a layer of solid rock with no cracks or pores. Aquiclude is a geological formation that may store water but does not transmit it, or has very low permeability, preventing water from moving through it, like clay soil. Aquitard is a layer with low permeability. It can transmit water, but at a much lower rate compared to an aquifer. Think of silty clay layer. It can hold some water, but it allows water to flow through it very slow. Aquitard can act as a confined layer for aquifer, separating them from other water-bearing zone. But indeed, we know what is aquifer. It is a layer of rock or soil with high permeability that can transmit and store large volume of water like sand or gravel that allow water to flow through them easily. So aquifers are our primary source of groundwater. Imagine a layer of cake, a rock and soil. Confined aquifer is like filling in the middle sandwich between two slices of impermeable rock, like aqueducts or aquifers. These impermeable layers trap the water into the aquifer under pressure. Confined aquifers can be quite deep underground. The water in confined aquifer is under pressure, and when well is drilled, the water can be rise up and pressure can occur. It's called also artesian wells. Unconfined aquifers is like an open sponge buried underground. Unlike confined aquifer, they are not sandwiched between impermeable layers. They are typically composed of permeable materials like sand, gravel, or uncompacted rocks that allow water to flow through them readily. The top of the saturated zone in an unconfined aquifer is called the water table. The water table is not fixed. It rises during periods of recharge like heavy rain or dry season or pumping from wells. Now it's time to explore the aquifer and well performance test, which are crucial tools for hydrogeological and water resource manager. Think of an aquifer and well performance test are a checkup for your groundwater resource. Aquifer tests are focused on assessing the hydrogeological behavior of the aquifer itself. They provide information about the aquifer's capacity to store and transmit water, such as transmissivity, hydraulic conductivity, and storativity, like measuring its ability to store and transmit water. On the other hand, well tests are like checking the health of a specific well. These tests focus on evaluating the performance and characteristics of a specific well. They provide information about the well capacity to extract water efficiently, such as its pumping rate, specific capacity, and drawdown. There are some key terms to remember. Drawdown is the drop in the water level in a well caused by pumping. Imagine a pump being lowered into a well. The drawdown is the difference between the water level before lowering the pump and the water level after pump is operated. The specific capacity is measured of well efficiency. It tells us how much water the well can produce for a certain amount of drawdown. Finally, safe yield is the golden rule of groundwater extraction. It's the maximum amount of water we can take from the aquifer without compromising its future ability to store and transmit water. During a well test, we measure key parameters like pumping rate, drawdown, and specific capacity. The pumping rate tells us how much water the well can produce in a given time. Drawdown, as mentioned before, is the drop in water level caused by pumping. Specific capacity combines these two parameters. It's a measure of how much water the well can produce for a certain amount of drawdown. To conduct a well test, we use a combination of tools like pumps, flow meters, pressure gauge, and water level loggers. The data collected from these instruments help us to assess the well efficiency and its potential for sustainable water production. Aquifer tests are like taking an X-ray of an aquifer. They go beyond the wall itself. It reveals the hidden properties of the aquifer that govern groundwater flow and storage. Similar to well test, we measure pumping rate, drawdown, and specific capacity. However, aquifer tests go a step further by estimating aquifer properties like transmissivity, hydraulic conductivity, and storativity. A key element of aquifer test is the use of observation well or piezometers. These wells act like monitoring water level change in the aquifer caused by pumping from the main well. By analyzing the drawdown in both the pumps and observation wells, we can understand the extent of the cone of depression and how the aquifer respond to pumping stress. Aquifers and well tests involve a series of steps to collect data and assess performance of the well and the aquifer. Pre-test preparation. Select the well to be tested. If conducted an aquifer test, drill one or more observation wells at a specific distance from the pump well. Install pump, flow meters, pressure gauge, and water level loggers in the well. Then measure statistic water level and start pumping water from the wells at a constant rate for a predetermined duration. Continuously monitor and record the pumping rate, water level in the pumped well, and water level in observation well. Data recording can be manual or automated using electrical data loggers. Post-test recovery. Stop pumping and allow the water levels in the wells to recover to their statistic condition. Continuous monitoring water level recovery in both the pump and observation wells. Then data analysis. Once the water level have stabilized, download or compile the data from the recording instruments, analyze the data using appropriate method. Once we have collected the data from the aquifers and well test, it's time to analyze to extract the valuable information. There are various methods for analyzing tests, and the choice of method depends on the type of test conducted and the specific parameters we want to determine. Thies curve analysis or Thies method. This graphical method is widely used to analyze aquifer test data, particularly for confined aquifer. It involves plotting drawdown data versus time on a log-log scale and matching the data with a Thies curve to estimate aquifer properties like transmissivity and storativity. Cooper-Jacobs straight line method. This graphical method is another common approach for analyzing aquifer test data, often used for unconfined aquifer. It involves plotting drawdown data on a semi-logarithmic scale, time on a logarithmic scale, drawdown on a linear scale. Type curve matching. This graphical method involves matching the test data with a set of theoretical curves, type curve, that represent different aquifer properties. By overlaying this data, an appropriate type curve, we can estimate aquifer characteristic. The Thies or Thies curve is a graphical workhouse in the world of aquifer tests. It's a power tool for hydrogeological to unlock the secrets of aquifer hydraulic properties by analyzing drawdown data. This method involves plotting drawdown, the decrease in water level caused by pumping, on the y-axis against time, the duration of pumping on the x-axis. But here is the twist. Both axes are scaled logarithmically. This log-log scale brings out the hidden patterns in the data, allowing us to compare it with a standard curve or name it Thies curve. The Thies curve analysis relies on two key parameters or assumptions. The pumping rate must be constant throughout the test, and we need at least one observation well to monitor drawdown away from the pump well. Let's take a closer look at the Thies curve analysis graph. By visually comparing the patterns of the data points with the Thies curve, we can estimate the real-world properties of the aquifer we are testing. The better the match between the data and the Thies curve, the more confident we can be in our interpretation. The Thies curve analysis is a powerful tool, but it's important to remember an assumption and limitation. Now let's delve into the world of well design and construction. Well design involves a series of stages: site assessment and exploration, soil profile development, drilling operation, case installation and stabilization. Then we have screen placement, gravel pack installation, pump installation, testing and disinfection. Well design considers various parameters to meet specific needs. Borehole depth for shallow wells 10 to 30 meters, for deeper wells 100 until 1000 plus meters. Borehole diameters is typically range between 10 to 30 centimeters, while piezometers or observation wells have a smaller diameter from 5 to 10 centimeters. The well drilling method is chosen based on the specific characteristic of the subsurface geology. So we have percussion drilling suitable for hard rock formation and deep wells. Rotary drilling uses a rotating bit to excavate the soil or rocks for shallow aquifers. Cable tool drilling, traditionally used for drilling through hard rock formation like limestone, can reach depths of up to 300 meters. Also, we have air rotary drilling, use compressed air to circulate cutting out of the borehole, can reach depth exceeding 3000 meters. Reverse circulating drilling, utilize compressed air to lift cutting back to the surface through the center of the drill stem, can reach depth up to 500 meters. Mud rotary drilling employs drilling mud to circulate cutting cool the drilling bit and stabilize the borehole walls, can reach depths up to 1000 meters. Once a well is constructed, we need a way to lift the groundwater to the surface for use. Here we will explore various groundwater pumping methods, from traditional hand pumps to modern motorized options. There is a range of groundwater pumping methods available, each suited to specific needs and application. Hand pumps are manually operated pumps, ideal for domestic use in remote areas or where electricity is unavailable. They typically have lower pumping rate, 0.1 to 0.15 cubic meters per hour. Dug well pumps These pumps are used in conjunction with dug wells, which are the oldest and simplest form of well construction. It's often made from rope operated, have moderated pump rate 1 to 5 cubic meters per hour, and are suitable for agriculture or small scale irrigation purposes. Motorized pump, these pumps are powered by an external energy source like electricity, solar panels, or windmills. They have offer highest pumping rate 5 to 200 cubic meters per hour. Hand pumps are a simple and reliable technology for extracting groundwater in areas with limited access to electricity. So hand pumps are commonly used in rural settings, in rural communities where grid electricity might not be available. Main components consist of riser pipe, a cylinder assembly with a piston and valves, a foot valve at the bottom of the rising pipe, a pump head with handle for manual operation, and connection rods. Common types including Afri-Dev hand pump and Indian Mark II or III hand pumps. Lifting capacity can typically extract water from depth up to 50 meters. Dug wells are the most basic form of well constructed, and they have been used for centuries to access groundwater. It's the oldest and simplest method, and main components consist of a well shaft, a lining to prevent collapse, a well cover to prevent contamination, a platform for access, a gravel pack around the bottom to improve water flow, a rope and bucket for lifting water, and designated protection zones around the well to minimize contamination. Pumping methods are used in conjunction with a simple rope. Lifting capacity similar to hand pumps. Motorized pumps are the workhorse of modern groundwater extraction. It's advanced pumping methods, and main components consist of an energy source like electricity or solar panels, a pump unit, and connection pipes. Common types motorized pumps can be powered by various energy sources. Electrical pumps are the most common, but solar-powered and wind-powered pumps are gaining popularity in areas with limited access to electricity grid. Now that we have explored well construction and pumping methods, it's time to delve into groundwater treatment. Groundwater can be classified into three main categories based on its salinity level, which is a key factor in determining the treatment requirements. Fresh groundwater, low mineral content. Brackish groundwater, medium to high salinity. Saline groundwater, high salinity. Even though classified as fresh, groundwater can still contain dissolved minerals or elements that require treatment depending on the specific application. Hard water that has high concentration of minerals like calcium and magnesium, which can cause problems like scale buildup in pipes and applicants. Water softeners are commonly used to address hardness. Sulfate-rich groundwater in some areas may have elevated level of sulfate, which sulfates are generally not harmful in low concentration. They can impact an unpleasant taste to water at high level. Treatment options include reverse osmosis or anionic exchange ionic exchange. Ion and arsenic-rich groundwater. Groundwater can naturally consist of iron, fluoride, or arsenic minerals. Water aggressivity refers to the tendency to dissolve or deposit minerals, particularly calcium carbonate, which is a common component of groundwater. The saturation index, or SI, is a helpful tool for understanding water aggressiveness. Calcium carbonate is a common mineral found in groundwater. It can either dissolve in water or come out of solution and form scale deposit on pipes and fixtures. Solubility index, or SI, indicate whether calcium carbonate will dissolve or precipitate. A specific pH value exists known as the pH saturation, where the water is neither aggressive nor scale forming. The SI is calculated by subtracting the pH saturation from the actual pH of the water. So SI should be equal to pH minus pH saturation. SI value of 0 indicate a balanced state water, while greater than 0 indicate oversaturation and potential for deposition, and less than 0 indicate an undersaturation with no risk of deposition of calcium carbonate. Aeration is a water treatment process that involves introducing air or oxygen into the water. It offers several benefits. Removes undesirable gases. So aeration helps remove gases like hydrogen sulfate, which can cause unpleasant odors and taste. It can also remove volatile organic compounds, VOCs, that may present in the groundwater. It is necessary to adjust the pH. So aeration can help adjust the pH of water by promoting the release of carbon dioxide. So here there is a relation between carbon dioxide and pH based on the following formula. pH equal 6.4 plus logarithm HCO3 over CO2. Oxidation of iron and manganese. Aeration can also assist in oxidizing dissolved ferrous ion, Fe2 plus, and magnesium manganese to their soluble ferric and magnetic form. This oxidized form can then be easily removed through filtration. Groundwater is a precise resource and sustainable practice are crucial for its long-term availability. There are three main categories of aquifer discharge method: artificial or man-made method, natural method, or riverbank filtration. Riverbank filtration means pumping water inside the soils located closer to river streams. Aquifer recharge offers multiple benefits, maintaining sustainable groundwater level. We ensure the long-term availability of these vital resources for future generations. Improved water quality. Natural filtration process that occur during recharge can enhance groundwater quality, reducing the need of extensive treatment, supporting base flow in rivers and streams, which is the continuous flow of water in rivers and streams during dry period. This is crucial for maintaining healthy aquatic ecosystem. Thanks for watching my video for today, and I hope you learned something valuable. See you next time.